Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. Sit back and relax while we unfold your brain with weird and wonderful science. I'm Ian Woolf. On this edition, Maria Cunningham talks about her search for little green molecules in space. But first, NASA makes a big wet announcement. Big NASA moon announcement announced. No, they didn't find a monolith, or alien life, or green cheese, but the moon is a bit wet. NASA's Stratospheric Observatory for Infrared Astronomy, SOFIA, has found that water exists on the moon. Not just in icy shadows, as we believed, but even on the sunny side of the moon. Specifically in Clavius Crater, one of the largest craters visible from Earth, located in the moon's southern hemisphere. There's not a lot of water there, but we didn't expect any at all. For comparison, the Sahara Desert has 100 times as much water as Clavius Crater. SOFIA, the Strategic Observatory for Infrared Astronomy, is a modified Boeing 747 SP jetliner with a 106-inch diameter infrared telescope. The aircraft flies above 99% of atmospheric water to make its infrared observations. In 1969, when the Apollo astronauts first set foot on the moon, we thought the moon was all dry. In the 21st century, NASA's Lunar Crater Observation and Sensing Satellite confirmed ice in permanently shadowed craters around the moon's poles. Without an atmosphere, any water on the moon should just evaporate if it's in the sun. Something is generating the water, and something must be trapping it there. Some of the educated guesses are that micrometeorites hailing down on the lunar surface, carrying small amounts of water, could deposit their water on the lunar surface on impact. Or perhaps the sun's solar wind delivers hydrogen to the lunar surface, causing a chemical reaction with oxygen-bearing minerals in the soil to create hydroxyl molecules. And then radiation from the bombardment of micrometeorites could be transforming these hydroxyl molecules into water. This water could be trapped in tiny bead-like structures in the soil that form out of the high heat created by micrometeorite impacts. Or the water could be hidden between the grains of lunar soil and sheltered from the sunlight. Follow-up flights of the infrared telescope will look for water in other sunlit places on the moon, and during different lunar phases to learn more about how water is produced, stored and moved across the moon. The data will add to the work of future moon missions, such as NASA's Volatiles Investigating Polar Exploration rover, VIPER, to create the first water resource maps of the moon for future human space exploration. Yep, it can't just be about knowledge and exploration, it's got to be about mining exploitation. Mining lobbyists just won't let us be. The paper was titled Molecular Water Detected on the Sunlit Moon by SOFIA and was published in the journal Nature Astronomy. You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. Little green molecules, the stuff of life? Maria Cunningham is a radio astronomer in the School of Physics at the University of New South Wales, where she searches for molecules in the interstellar medium, looking for molecules that might point to life outside Earth. I spoke to her by Zoom to her home in the Blue Mountains. You can occasionally hear birds and dogs in the background. I began by asking Maria how she got started as a radio astronomer.
I actually did my PhD at the CSIRO Division of Radio Physics, which ran the Australia Telescope National Facility. So I'm a radio astronomer, and my research is basically anything to do with the interstellar medium, which radiates at radio and millimetre waves. I'm particularly interested in molecules, because with molecules I can work out how stars and planets form. And I also say that a hobby of mine is looking for little green molecules, the sort of stuff of life. Not little green men, but little green molecules. I have the slightly unusual trait of doing a PhD with 4 children. Like everybody, I thought cosmology was amazing. I didn't know I wanted to be an astrophysicist because I didn't know this was a possibility when I was at school. I don't think anyone really does unless they know an astronomer, or maybe if you've spent a lot of time watching. I guess these days, if you watch Karl Kruszelnicki or people like that, the movie Contact, perhaps it's more obvious that these things are a possibility. But it was never something that came even into my horizon, is become an astronomer. I think if it was possible, I would have probably jumped at the chance. Yes. In fact, years later, I had a good friend when I was at school who used to build amplifiers and all sorts of things. He had an electronic shed in his backyard. And I remember at a school reunion when we were all in our 30s, and I told him what I was doing. He said, "Oh, you've done what I always wanted to do." And he was a radio engineer by that time, of course. And I said, "Wow, even back then you knew this existed. I wish I had." So it was quite a circuitous route. But anyway, I decided I wanted to do a PhD in physics because I really love research and I find physics fascinating. And I then discovered, I guess as a lot of people did at the time, that one of the premier areas in Australia when I was doing my PhD in the 90s was radio astronomy. You know, it was, I think, often described as the jewel in scientific Australia's crown, that we really did punch a long way above our weight in radio astronomy, particularly with the synthesis imaging, where you can take a number of radio telescopes, point them at an object and synthesize a much larger telescope. And
that's quite an amazing idea, isn't it? That you can join lots of radio telescopes together into a giant one.
Yes, Fourier transforms are the magic that allows you to do it. So you can actually take the radio signals coming separately to each telescope, and then you can use the mathematics of the 19th century Joseph Fourier, and you can transform those signals into what you would see. So there's 6, the Australia Telescope Compact Array in Narrabri. They're spread out along a 6-kilometre baseline, and they simulate a telescope with a diameter of 6 kilometres.
I mean, it's amazing.
Yes, it really is. That with a little bit of mathematics, and of course at the end of the day, all science, but particularly physics and astrophysics, comes back to mathematics and careful observation. You need them both together. But at the end of the day, if you go looking in the toolbox of mathematics, you'll find something that can actually help you to develop these new ideas, which can tell us so much more. For the other sciences, biological sciences, etc., statistics is an amazing tool. And of course, that goes back to the work of Gauss, who, as far as I know, was commissioned to actually do his groundbreaking statistical work to help his mentor, who was a prince, I think, possibly a count or a duke, work out the gambling odds.
That's right. That's an important story in the
Carl
history of
Friedrich
mathematics.
Gauss, yes.
And it worked, of course.
And it worked. The whole thing was that it worked. And I remember actually being really delighted when I did my first subject in statistics and realised that you could take all this data, which was just a mess, and that you could run some sort of t-test, some sort of statistical test, and you could find out whether there was a signal there or not. And of course, with big data, this has just become absolutely mainstream now. So,
I wanted to ask you. You were talking
yes,
earlier about how you can make a lot of little radio telescopes behave as if a really big one with the mathematics of
yes,
Fourier. Is there a limit to that or a constraint other than the size of the Earth?
there, no, no, there's no constraint other than the size of the Earth. And in fact, you might be able to do a little bit better on the moon. The moon's curvature, because it's smaller, would be worse, but you could have larger structures because of the lesser gravity. And I was really interested yesterday to see an announcement that there's an alliance of organisations in the US who are now planning for 2024 to actually send people to live on the moon for a small while. And I thought, yep, yeah, one of these days you give an astronomer an opening and they'll take several light years. And so I can just imagine if I thought of it, there was astronomers around the world who were saying, okay, so how big will the rockets be? How many components do I need for my radio telescope? And so you'd get better sensitivity. You wouldn't get a longer baseline. For longer baselines, you need to go out into space. And to put it a bit more in terms people can understand, you need the telescopes to be able to see the same bit of sky at exactly the same time. And so we can make baselines, as we call them, one telescope here in Australia and one telescope in South Africa, between here and South Africa. But there's about a 2-hour overlap where the two telescopes can see the same part of the sky. And this is a constraint because one of the important things about VLBI, very long baseline interferometry. I say it all the time. I don't know think about how to spell it out. One of the constraints with that is you need to look for a long period of time as the Earth rotates, because as the Earth rotates, the baseline between the two telescopes, as seen from space, changes. And when you have a slightly different baseline, you see slightly different spatial structures. And given the people who watch these podcasts are probably very interested in science, one of the good ways to think about this, and of course, if you've never heard of it before, just look it up on the internet, a demonstration of Young's double slit experiment. So you shine a laser light through 2 tiny pinholes. The Young's double slit experiment, for anyone who's seen it, you shine a laser light through 2 slits and you end up with a very nice stripy pattern on a nearby screen or wall. The stripes are evenly spaced and they're spread out quite a way. When you're using a radio telescope, the radio telescope is actually detecting that pattern. So it's like you put your radio telescope on the wall and you detect that stripy pattern, you put it through a Fourier transform and you get back the size of the double slits and the spacing between them. And we're doing that with space. So if you're looking at a distant quasar, then with a distant quasar, you're not going to be able to see what it looks like. You just want the light from it to understand what it's doing. So you just want the longest baseline you can possibly get. If you're looking at a molecular cloud, which is the sort of stuff that I look at, you've got things of all different sizes. So you've got the diffuse gas, which is not doing much. You've got clumps, which have lots of nice organic molecules. And inside that, you've got stars and planets forming. And so you want as many different baseline sizes as possible so you can reconstruct as many different spatial sizes as you want.
Right. And what sort of molecules are you finding?
Right. Well, this is one of the things that blew me away when I first discovered it. Organic molecules, which just basically means molecules based on carbon, but they're also based on carbon, oxygen and nitrogen, which are 3 of the more common elements in the universe. But those are also the things that make up the molecules of life, including proteins. So, and we have not yet found an amino acid. I've been heavily involved in the search for glycine, which is the simplest amino acid. We have not yet found that in the interstellar medium, but we know it exists in comets and we're pretty sure it's out there. So I've I think one of my most famous scientific discoveries was the non-detection of glycine. Someone thought they detected it. It was heartbreaking. It's one of those moments where I'd done this. I was so proud of myself. I've got a couple of years of telescope time and hours looking at a couple of sources where we thought glycine should be. And then I go to a conference and someone puts up a poster saying, glycine detected in the interstellar medium. And I thought, oh dear. And I thought, oh, well, never mind. We'll reduce the data. We'll look at it. And then we can at least get some more information about it. But what we found was that they hadn't detected it. They had detected a single line. Spectral lines are just like this radio station we're listening to at the moment, or if you're on the podcast, presumably... let's try that analogy again. It's like when you listen to the radio. You tune in to a particular frequency, and you're associated with community radio on Kangaroo Island.
I'm
Right?
associated with community radio around Australia, the Community Broadcasting Association.
Right. Yeah, no, that's fantastic. I did an interview with 2SER a while ago, and I saw they were on your list, and the Blue Mountains, which is where I originally came from, is on your list. So when you tune into your community radio station, you dial up a particular frequency. That's what our molecules do for us. They transmit at specific frequencies, which are governed by the rules of quantum mechanics, and we can tune our radio telescopes to those frequencies. The trick for detecting a molecule is you need about 4 of the molecule's known frequencies. So if you wanted to know if community radio existed on the Earth, if you just detect the one from Kangaroo Island, you'd say, that's interesting, but that's just one instance. But then if you find the Blue Mountains and 2SER and the rest of it, you can say, yeah, they have a community radio network.
And of course, that's what they were trying to do with looking at phosphine on Venus.
Oh, absolutely. That, I was lucky enough to know the people involved in that. And that was a really, really careful piece of scientific analysis. And in fact, when I first saw it, because I know of the big surveys they've been doing, I thought, oh, they've just picked this up. Because you go through, you find all the lines and you try and do some identifications. But in fact, they'd specifically set out to look for phosphine as a biomarker. So they had shown that chemically it should only, in a non-hydrogen dominated atmosphere like Venus, the only known way to do it is by biological processes. And so they knew that if we found phosphine in Venus's atmosphere, that would be exciting and it would be a biosignature. Now, no one's claiming that this is life, but they're saying it is a biosignature and you can detect it on another planet, and they knew the frequencies they were looking at. And at the moment, it's only one transition, but they've done a good job of eliminating just about everything else. And of course, they'll confirm it quite soon.
Yes, well, there's various missions to fly by and have a closer look at the atmosphere.
Yes, and that's the nice thing. Venus is close enough that, given time, we can actually get a mission to go there and take a sample.
Which will be, I guess, one of the clearer indications, and then they've got to work out what's making the phosphine.
That's right. And of course, the most exciting thing would be if what's making the phosphine is in fact bacteria which are in the 40 to 60 kilometre, or not even bacteria, some sort of very primitive viral type thing perhaps, but bacteria would be, oxygen-producing bacteria would be the most likely thing, and you'd need a circulation of these things, so you need a reservoir a bit further down, something that can lay dormant, and then the circulation currents bring them up into the 40 to 60 kilometre zone, which has a very nice temperature of around 30 Celsius, and then you can reactivate them. And so you need something like that, a constant system. But yes, that would be very, very exciting. And I'd be very surprised, given how common organic molecules are out in space, specifically very complex organic molecules, including the stuff we need for life. I'd be very surprised if the Earth is the only place where it got going to the primitive stage.
And I was reading the astronomers currently think that about 1 billion years ago, Venus wasn't as hot and acidic as it is now, that it was closer to the sort of 30 degrees nicer environment that could support life.
Very much so. So this could be a remnant of something that got going on the surface of Venus, and it's the only little bit that survived. And in fact, Mars was far more conducive to life when it first formed. Before it lost its atmosphere, it just didn't have the gravity to keep the atmosphere going. So yes, that is almost certainly possible. The other piece of evidence we have on the Earth of the smoking gun for life forming easily is the fact that we have evidence for life going back to about 4 billion years, almost the moment when the Earth cooled down enough for these molecules to get together, because if the surface is too hot, then the molecules just can't bond. They keep being destroyed by the heat and the UV radiation. So yeah, that is another reason why I wouldn't be surprised if this is something to do with life, but you'd want a lot more evidence before you were sure of that. I should also say, on the balance of probabilities, it will probably turn out to be some chemical process that's not life-based that we don't know about yet. So whatever happens, it'll be interesting.
Absolutely. I mean, the irony is that from the way I was reading the story, they were going to use phosphine as a biomarker to look on exoplanets, and they were going to use Venus as a baseline of what a planet without phosphine looks like.
That's right. Yes, absolutely. And someone I know quite well, Jessica Dempsey, is the Deputy Director of the James Clerk Maxwell Telescope, the JCMT in Hawaii. And I was reading her comment when she was saying that when she first saw the line on the screen that Jane Greaves had sent her, she just stared at it for a minute or two and thought, this can't be here. This can't be here. So it's one of those wow moments in science that I think very few people actually get. Science usually moves, a lot of hard work, little bits at a time, putting a big picture together. But if you're lucky, you get one of those wow moments.
It must have been just jaw-dropping to see yourself proved wrong in a way that you really would like.
You would like, that's right. You wouldn't dare to hope for it. You wouldn't dare to hope for it. That was something that's quite close to the sort of work that I do. And in fact, the interview I did for 2SER a few weeks ago was actually about phosphine, and that was quite nice too. It gave me an excuse to take a step back from my normal day-to-day life and look a bit more closely into it all than I would have otherwise. And so that's quite nice. And I thought one of the best quotes I saw was from a British astronomer who said, well, it's not life, it's not even a smoking gun, but there's a distinct whiff of cordite in the air. And I thought, that's a very nice way to put it.
Even if you put aside the excitement of ever possibly finding some sort of non-terrestrial life, it's not that common these days to have totally unexplained chemistry.
No, it's not, because we know a lot more than we did 20 or 30 years ago. The discovery of molecules in space came as quite a surprise, because you can actually show that with the conditions in the interstellar medium, the stuff between the stars, molecules can't form and they can't stay together if they do form. Now, what we hadn't taken into account was that you get certain regions where it becomes so dense that the molecules are shielded from the nasty radiation of space. And we have a different sort of chemistry. Normally, in chemistry, you need 3 atoms to collide, even if only 2 of them bond to form a molecule. So there's always a third body in the collision. Out in space, you can do it with something called ion molecule reactions. And all of that only developed after the detection of molecules actually out in space. And since then, we've got very good laboratories on the Earth now, with a little astrochemistry group at the University of New South Wales that really does split between astronomy and chemistry. And we also have the Centre for Astrobiology, which involves chemists, astronomers, biologists and geologists. And that's where a lot of the interesting work's done. I'm just very purely on the astronomy side, but some of my colleagues are definitely looking at the planetary science, and that's where Jane Greaves and her team were coming from.
No, it's amazing work. I spoke briefly to some of your colleagues at the Centre for Astrobiology about the launch of the rover to look for life on Mars.
Yes. So that will be a very interesting project. Over the years, there have just been one or two experiments that have given a hint that there may be unicellular life on Mars. And basically, I think what you really need to do, and I must say, I'd actually have to look very specifically at the rover experiments, so I'm just talking in general terms here. But what you generally do is have a laboratory on board the spacecraft which can pick up a sample of soil and find out what's in it. So we found ice crystals on Mars. We found some interesting carbon chemistry that produced some oxygen a long time ago. Probably chemistry we don't know, but I would expect something will come out of this. My best guess, and this is not my own guess, is that life will be found if you could go quite a few kilometres under the Martian surface where there's almost certainly water, liquid water, because as you go down mines, apparently miners know this, it gets very hot the further you go into the earth. I suspect you might find some sort of bacteria of some sort down there, some sort of extremophiles, etc.
That was the first part of my interview with radio astronomer Maria Cunningham from the University of New South Wales, talking about the search for life off Earth. Listen next week for tales of the search for extraterrestrial intelligence and multiple universes. You'll soon see the video of this interview and many others on the Diffusion YouTube channel. Subscribe and like at youtube.com/c/Diffusion Radio. And that's all from us this week on Diffusion. Are you a scientist, artist, biohacker or maker who'd like to be interviewed about your work? Would your company like to sponsor Diffusion? Send your contributions, opinions, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com. Please like the Diffusion Science Radio page on Facebook and rate the show on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. The news music was Rhinos theme by Kevin MacLeod of Incompetech.com. I produce Diffusion, which is broadcast around Australia to 28 stations on the Community Radio Network, including Radio Blue Mountains 89.1 FM in New South Wales, 8CCC in Alice Springs and Tennant Creek, 2 MVR in Nambucca Valley, 3 MBR in the Mallee Border districts of Victoria and South Australia, City Park Radio 7LTN in Launceston, Tasmania, and 2XXFM in Canberra. Diffusion is now narrowcast on Indigo FM 88 in northeast Victoria. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm. Subscribe to our podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos and videos about this week's show. If you enjoyed the show, you can explore more than 1,000 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Make a donation through paypal.me/Ian Woolf. Join my patrons at patreon.com/diffusionradio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits. Photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.